Hello, my fellow YouTubers. This is Roy back again. I need to go over a couple more things that I didn't cover last night on my previous video. I think we left off at octaves. We'll go back into Schumann. I think I covered just a little bit of it, but this was important that you guys need to know about. So in regards to the Schumann, when converted into sound waves, 7.83 is a flat B2, 2 octaves below the lowest note on a piano. The electric powers hum in USA at 60 hertz. I know you guys across the pond are in 50 hertz. 60 hertz is the 9th overtone of the earth, and the loudest note from space is B1 or a deep B. The Earth behaves like a gigantic electric circuit. Its electromagnetic field surrounds and protects all living things with a natural pulsation of 7.83 hertz. On average, the so-called Schumann resonance. So when you dig into a little deeper, we're going to cover this so you guys have a better full understanding, and you can snapshot that if you want, and you can also snapshot that if you want so you can read it back to yourself. My handwriting is not the best, but it's legible. So the Earth's circumference is 24,901 miles. To us over here in USA, 1 mile is 5,280 feet. At any given moment, about 2,000 thunderstorms roll over Earth, producing some 50 flashes of lightning every second. Each lightning burst creates electromagnetic waves that begin to circle around the Earth, captured between the Earth's surface and a boundary about 60 miles up. Think about that, 60 miles up in the air we're talking. Some of the waves, if they have just the right wavelength, combine, increasing in strength to create a repeating atmospheric heartbeat known as the Schumann resonance. This resonance provides a useful tool to analyze Earth's weather, its electric environment, and to even help determine what types of atoms and molecules exist in the Earth's atmosphere. The waves created by lightning do not look like the up and down waves of the ocean, but they still oscillate with regions of greater and lesser energy. There's your difference in potential. These waves remain trapped inside the atmospheric ceiling created by a lower edge of the ionosphere, a part of the ionosphere filled with charged particles which begin at 60 miles up into the sky. In this case, the sweet spot for resonance requires the wave to be as long as twice or 3 times as long as the circumference of the Earth. We're almost through, guys. This is extremely low frequency wave that can be as low as 8 hertz, some 100,000 times lower than the lowest frequency radio waves used to send signals to your AM/FM radio. As this wave flows around Earth, it hits itself again at a perfect spot, such as that the crest and the troughs are aligned. Viola waves acting in resonance with each other to pump up original signal. Very important. I wanted to go over that with you. And on the next video, we'll start throwing some numbers together on this side, and we'll look at the frequency, of cone A and cone B, and then we'll look into the octave. And when I talk about octaves, we can go back to the beginning here. Is a wave resonator is a secondary coil wire, must be a quarter wavelength at the resonant frequency. And a wave resonator tube, closed at one end and open at the other. The walls are rigid end of a tube, confines a body of air within the resonator cavity. Under certain conditions, this body of air can be brought to a state of resonance. So what we're talking about is the cavity that's inside the conical cone. So the top and the bottom act like waveguides. And we'll get into more notes, and we'll get into doing some testing. And what we'll do is we'll hook up this to an oscilloscope, and it's ready for testing, other than I have to put the primary bifilar and two primary bifilers in place, and then we can hook it up to an oscilloscope. Don't know when I can get to doing that, but you'll find out when I post the video. And we'll look at the wave that we're producing, and we'll do it in dual channels, so the top and bottom are we'll see the difference in the waves, and we'll add resistance to one side of the conicals, which will allow resistance would be like adding more wire. And we'll start off with 1 ohm difference in the two, and then we'll look at the wavefront, and then we'll also look at one of the pickups and see what it's producing and the wave fronts of what it's producing. So this is going to be interesting tests that will transpire shortly. Peace out, my brohams. Leave your comments.